Hello everyone. Given that we have basically reviewed our algorithm for circuit analysis in the past lectures, now we're going to start using the algorithm on more and more circuits. You start with relatively simple circuits, resistive in nature, meaning that the source, there's a source of energy or more than one source of energy connected to a network of resistors that are connected to each other in one way or the other, and we try to calculate all the voltages and currents in that circuit. This is a relatively simple one. We start with this one. We then define the concept of equivalency, and then we move on. So in this circuit we have a source of energy. In this case, specific case, we have a voltage source with the potential difference across the two terminals equal to Vs. That could be any number, connected to 3 resistors, and this specific configuration of resistors connected to each other is called in series. So we have to get used to some of the terminology that is common in electrical engineering, one of them being when the components are connected to each other in a certain way, they're called in series to each other. So what that means is that the current that is passing through one is actually the same current that passes through the next, and in that case the two devices are called, or the two components are called in series to each other. So why do we then say that's the case here? If we identify this as a node and then this one as a node, and then this is another node, which is the first thing that we're going to do, and then we said we're going to pick one of them as our ground, or 0 volts. Then we define voltages and currents. I'm going to define currents first in this case to make my point. So if I define current I1 and then I2 and I3 for these 3 components, and then write KCL for that node, I know that the current that goes into that node is I1, the current leaving is I2, and the two have to be equal to each other. Therefore, the current passing through R1 and R2 are the same. You can do the same for R2 and 3, and actually you can do the same for the voltage source and R1. Given that, we know there's only one, it's the same current that is passing through all the 4 components in this circuit, and therefore all of these components are called to be in series with each other. Okay, let's go back and start from the beginning. So I identify the nodes and start labeling the nodes. Now, I'm going to ask you to basically skip certain steps in the process carefully, so that we actually reduce the number of equations that we do at the end when we do the math. And as you practice in these shortcuts, you get more comfortable doing the same in the future. So we start by defining our ground, and then for the top node, usually I would ask you to call this V1, and then later on you're going to write an equation for this component, and that equation would tell you that V1, the potential of the positive terminal, minus V potential of the negative terminal, which is 0, is equal to Vs. If you write that equation for that power supply, you immediately figure out that the potential on top of the voltage source would be Vs. So we can actually run that in our head, and at the time that I'm trying to label that, I can say that's Vs. So generally speaking, if you have a source, and this is V plus, and this is V minus, this is Vs, since you know V plus minus V minus is equal to Vs, if you have labeled V minus, you can always label V plus as being Vs, the potential difference, plus V minus, which is what we have done here, right? So V plus, the voltage on top, is 0 plus Vs. So you can always do that in your head, and with that, what you have done is that instead of introducing a new variable in your circuit, V1, you've actually used a known value, which then reduces the number of equations that you have by 1, simplifying the math that you're going to do. Now, I'm going to keep calling this V1, V2, and now I'm going to start labeling the currents in the circuit. So if I call that IS, now the next thing that I can do is to run the KCL in my head for that node at the time that I want to label the current that is passing through the component. So IS goes in and I1 leaves, but I know IS has to be equal to I1, so when I label that, I can actually call this IS. Do the same for I2 and do the same for I3. So look at this. With skipping a couple of steps, or actually combining the labels with the process of writing equations for component and KCL, I have reduced the number of unknowns substantially. If I wouldn't do that, I would have 1, 2, 3, 4, 5, 6, 7 unknowns. But using the techniques or shortcuts that I just explained to you, I'm only dealing with 1 current and 2 voltages, 3 unknowns. So I'll reduce the number of unknowns from 7 to 3, which means that when I'm about to do the math, I will be doing, basically I will be trying to solve a set of 3 equations as opposed to a set of 7 equations. Okay, so next we're going to have to do KCL and equations for components. Now, I know that I've already done the KCL for all the nodes, so I can skip that step because I did that when I was labeling the currents through the components, and directly go to equations for components. When I'm doing equation for components, I know that I've done the equation for this component when I labeled that node VS, so there's only 3 components left. So equations for components, for the 3 components that are left, for R1, IS is equal to VS minus V1 divided by R1. Now, for R2, IS is equal to V1 minus V2 divided by R2. And finally, for R3, IS is equal to V2 minus 0 divided by R3. And we are done with the 2 first steps. I have to solve a set of 3 equations with 3 unknowns. So using the technique that I explained to you in one of the other lectures, I'm going to move these around to show you how you could do that using a calculator that inverses matrices. So this circuit, V1, V2, and IS are the unknowns. I'm going to move them all to the left. So the first equation would be V1 plus R1IS is equal to VS. The second equation would be minus V1 plus V2 plus R2IS is equal to 0. Finally, the last equation is minus V2 plus R3IS is equal to 0. So I've moved everything to the left. So now I can actually turn into its matrix equivalent. So we have the matrix. Let me clear this. Vector of unknowns equal to the vector of knowns. So the vector of unknowns I'm going to choose as V1, V2, IS. Vector of knowns would be VS, 0, 0. And the matrix, the multipliers for the first equation would be 1, 0, R1. The second row would be minus 1, 1, R2. Therefore, the last row would be 0, minus 1, R3. So using that, just simply V1, V2, Is is equal to this matrix 1, 0, R1, minus 1, 1, R2, and 0, minus 1, R3, inversed, multiplied by Vs, 0, 0. So if your calculator could calculate the inverse of that matrix, then multiply by that vector, you get the values for V1, V2, and Is. Now, I'm going to actually do this with hand. This is a simple set of equations that I'm going to try to solve with hand. So I can equate, basically get rid of current relatively easily. I can equate these two equations to each other, and then these two equations to each other, and that way reduce the number of equations to only 2. So V1 minus V2 divided by R2 is equal to V2 divided by R3. And when I equate those two to each other, Vs minus V1 divided by R1 is equal to V2 divided by R3. So the first is a result of these two being equal to each other. The second is a result of these two being equal to each other. So I have now two equations and two unknowns. So I multiply both sides by the denominator. In other words, I multiply this by the other side, this by the other side, and move them around. So R3 times V1 minus V2 is equal to R2 times V2. And here R3 times Vs minus V1 is equal to R1 times V2. So from this, I know that at this point R3 V1 is equal to R2 plus R3 V2. In other words, from this I know V1 is equal to R2 plus R3 over R3 V2. And from this equation, now I can replace R1, V1 with the value that I have over there and directly calculate V2 as one of the unknowns. So in other words, now I have R3 times Vs minus R2 plus R3 over R3 V2 is equal to R1 V2. Once I move things around, I can calculate V2, which ends up being equal to R3 over R1 plus R2 plus R3 V. Yes. Once I do that, I'll put that back in there, and I quickly calculate V1 to be R2 plus R3 divided by R1 plus R2 plus R3 Vs. And from these two and any of those equations, then, oh, sorry, I have to repeat this. So V1 is R2 plus R3 over R1 plus R2 plus R3 Vs. Now, from any of these two, I can calculate the current Is to be Vs divided by R1 plus R2 plus R3. And we're done. We have calculated V1, V2, and Is. So one of the results that is important for us in this discussion is actually the current that is passing through these three, which appears to be the voltage of the source divided by the combination of all three resistors, or the value of the resistors added to each other. So why is that important for us? We can at this point actually start discussing the concept of equivalency. So what does that mean? If I put a box around this part of the circuit and assume that this is a system, it's an electrical network, a system, and I want to define something that basically behave the same as these components connected to each other, but only is one component, right? In other words, if I take this box and replace it with a box that doesn't have these three components, but only one component, and both of these boxes behave the same, then I can say that these two boxes are equivalent to each other, right? So what does behaving mean in an electrical domain? Well, the way that any component behaves in electrical domain is a response to a signal that is, electrical signal that is connected to it. So if you apply a voltage and you see a certain current going through the box, that's the response of the system or behavior of the system. And that's exactly what we're doing here, right? We are taking a voltage source and connecting it to this box, and the response of that system, the box, to the voltage that I connect to it is actually the current that is passing through it, right? So that voltage divided by the current that is passing through it, the voltage divided by the current that is passing through it, is the equivalent resistance of that box. In other words, I can take that box, replace it with one box that only has one resistor in it, and I'm going to call that equivalent resistance of that box. Now, I want these two to behave the same, meaning whatever voltage that I connect to this one, if I take the same voltage connected to this one, I want to get the same current. So from this equation, you know that once I apply a voltage Vs to this box, the current that is going to pass through it is R1 Vs divided by R1 plus R2 plus R3. So if this box is going to behave the same, if I take Vs and connect it here, so if I take the same Vs and now connect it to this box, the current that is passing through it is actually very simple to calculate, right? We know that there's this basically a simple Ohm law. The voltage across this is Vs. The current that is passing through it is going to end up being Vs divided by the resistance, right? So Vs divided by R equivalent has to be equal to the Vs divided by R1 plus R2 plus R3 for these two boxes to be equivalent to each other. If that's the case, then R equivalent has to be equal to R1 plus R2 plus R3. So when you have resistors connected to each other, you can actually equate the same response coming out of those components connected in series to each other with what's one single resistor, with the value of resistance being all the individual resistors added to each other. And you can extend this calculation that we did here to any number of resistors. You obviously could do 2, then we did 3, you can do 4, you can do any number and you get the same result. So from this point on, if you are not interested in knowing what the voltages in between the resistors are, and you just want to know what happens if I apply a voltage across a bunch of resistors connected to each other. In other words, if you're only interested to know what current passes through a bunch of resistors connected to each other, all you need to do is to take that resistors and add the values of each one of those resistors to each other, and then you get the equivalent resistance, and whatever this equivalent resistance is going to give you as the current would be the same current that that box is going to give you. So we take components that are in series to each other, take their resistances and add them up and use that as the equivalent to that circuit. Obviously, when you replace that bunch of components with just one resistor, at that point you're losing all the information about the voltages that existed in between each component. They don't exist here, and this technique is only useful if you don't care about that information, and all you need is the current that is going to pass through the whole thing combined. With that, I'm going to stop and move on to the next discussion, which is the continuation of the same analogy, now for a different kind of connection of the resistors to each other. Thank you.